the third distribution that we want to talk about is related to Bernoulli distribution. So if you think about the story for Bernoulli distribution as throwing a coin, head and tail, then binomial distribution comes in when we throw more than one coin. Okay, so n refers to the number of coins we throw. P refers to the probability of success. That means each coin has has the P probability of showing the head, where head is success. And X here must be, all right, it cannot be anything else. X has to be the total count of successes in the n coins. Let me say again, X, the random variable, must be defined as counting the successes, the number of successes. Where's my cursor? All right. X must be defined as the number of successes in the n trials, n throws. Then X will follow binomial with n equals to 10, p equals to 0.2. Okay, so why am I being so particular about that? Because when you throw 10 coins, n equals to 10, when you throw 10 coins, okay, you might not be interested in the number of heads, right? You might be interested in how long the time it takes for all the 10 coins to settle, for example. And then that is a continuous random variable. That is not going to be binomial. So you need to measure or count the correct aspect of the experiment. Then you will get a binomial distribution. So what is the correct aspect? You are interested in counting the successes of n trials. Okay, so long story short is binomial, when you set n equals to 1, then binomial n equals to 1 comma p is the same as Bernoulli p. That is the relationship. So Bernoulli is a special case, you can think of it, of binomial distribution. So binomial, the n can go, of course, beyond 1, and that's the part where it gets more interesting. So when you throw 10 coins, and each coin, every single one of them, has the same probability of success. So they must be identical, because if one of the coin has a higher probability of success or lower probability of success, then binomial will fail. All right, so they have to be identical, and n must be of course finite. When n goes to infinity, that's that's not the case. When n is large in practice, like n equals to 1,000, n equals to 1,000,000, we are no longer going to be using binomial, because we will then use normal distribution to estimate what is supposed to be binomial. All right, so when n is large, we tend not to be using binomial distribution for calculation stability, because this involves factorial, n factorial, n choose x. Yeah, so all this will involve n factorials and n minus x factorials, and those numbers get very large into the millions, and then you take factorial, boom, the calculations will all get blown into very, very large values that are not very stable. So instead of forcing ahead with that calculation, we will then use normal distribution instead. But let's come back to binomial distribution. We require the counts, the number of coins, to be finite, to be identical. Each coin, of course, will be a two-state outcome, because each coin, after all, is a Bernoulli distribution. So you can think of binomial as n times Bernoulli distribution, right? In that sense, of course, not mathematical. And once you have that, then the rest will be done. So when do we do this? Well, you will, anytime you can apply Bernoulli distribution, and you need to do that multiple times, that's when you get to apply binomial distribution. For example, just now we were saying, should I buy or sell this stock? Given the current state of affairs in the stock market, should I buy or sell this stock? Now you're not asking, should I buy or sell this stock, right? You're asking, will I get returns? Will I, if I invest now in this stock, will I get positive returns, because sometimes you lose money. If you ask that question right now, that's two stage. Will I get return or lose money, right? So that's Bernoulli. But if you say, if I invest in these 10 stocks now, all right, how many stocks? What's the chance that 5 stocks will give me positive returns? What's the chance that more than 7 stocks will, 7, 8, or 9, 10, more than 7 stocks, 7 or more stocks will give me positive returns? If you ask that question, then you definitely are on to binomial distribution. But like I said, you have to count the right thing to apply binomial distribution. So let's come back to the same story here. If I invest in these 10 stocks now, then after that, you don't ask, what's the chance that 7 or more stocks will give me positive return? You ask, what's the chance that in total, my returns will be more than $10,000? Oh, that is a very different experiment. You're doing a very different measurement that doesn't necessarily follow binomial distribution. Yeah, because you're not counting successes. You're counting returns in dollars, which is a continuous measurement. Yeah, so you need to count the right thing. So a lot of times students get confused. I thought you're talking about 10 stocks, and I did that. And how come in the prior case, in part A, for example, you have to apply binomial distributions when the question asks, what's the chance that 7 or more stocks give positive returns? That, of course, is binomial. In part B, it's the same scenario. The question asks, what's the probability that the investor gets a total of 10,000 or more returns? 10,000 or more dollars in returns. And that is not binomial. That is complicated, right? So you need to ask the right question. Doesn't mean so it's not situation dependent. It's the measurement aspect dependent. If are you counting? Are you measuring? So what are you asking? What question are you asking? So you need to be very particular, very investigative. Then you are on to success.